So welcome everyone for the last day of the Young YEFC Create Correct program summer school. I'm very happy to have Paul Millar from DESY with us this morning. He will show us a bit or talk about FAIR and data management, which I think can be highly beneficial in our community where we're mostly intersectoral. So Paul, welcome. Thank you for taking time and go for
Thank
it.
you. Thank you. It's my pleasure to be here and to talk about to give you some information, insights into fair data, open data, and these kinds of aspects. So now I need to see if I can ask my computer very nicely if it will share. That's now coming up okay?
Yes.
Okay, good. So I've split this presentation into kind of mainly two parts. The first part and a short introductory part. This is where we're at the moment. This is just kind of letting things kind of putting things in context, and so that you see where I'm coming from when describing these things. So I work at DESY, Deutsche Elektron, which is a facility in the north of Germany. It's sort of historically and indeed still is a hydrogen particle physics laboratory. So it's from 1959, I think, was investigating particle physics. There was a lot of very useful science came out of that, but the main facility, the HERA facility, shut down in 2007. And since then, the focus has shifted in the hydrogen particle physics. It's shifted to working in collaboration with other facilities and various next generation particle physics activities. A lot of the focus has shifted, though, towards photon and X-ray, particularly X-ray analysis of materials. So this is, you can see at the bottom there. Hopefully, can you see my mouse pointer if I point? Does that come up on the?
Yes.
Yes,
okay,
yes.
Good. So I can point to things. That's nice. So at the bottom here you can see this is the Petra, which is the if you like the warm-up lap before particles were injected into the HERA facility in the HERA storage ring, and this we can generate very bright X-rays in these kind of buildings here highlighted in blue. These are the experimental halls where, as you can see on the right here, this is where we can do some analysis of the materials. So this is the Petra facility, Petra 3, and on the right here you can see the flash, which is a free electron laser. So this one's in a straight line, the Petra's in a circle. So this is sort of DESY has this kind of dual role. For myself, this is also something that's with me as well personally. So I've started off here at DESY as a Dcache developer, which is storage used to record data throughout the world, but very a lot of data, so very large scale, hundreds of petabytes at each facility typically. This is being used worldwide with the WLCG, so this was instrumental in finding the Higgs boson. And most recently, I was involved in Intertwin, which is federated data management there. But I'm also involved strongly with photon science. So this again is the dual aspect, where I was the technical coordinator for Expanse, which was a project on fair data in photon and neutron facilities. I'm currently the LEAP's IT coordinator for coordinating the IT activities in all of the European facilities. I'm also involved in OSCAR's EU-funded project, and I'm also sort of contributing to various metadata standards. So that's sort of my background. Here, just in a sort of a somewhat graphical representation, we had two projects, Expanse and Panos. These are really to sort of bolster or start the journey of moving these photon and neutron facilities towards producing public and fair data. So this was a journey we started 2018, 2019, Panos targeting the international facilities and Expanse targeting the national facilities. DESY is a national facility. We were actually coordinating the Expanse project, and I was technical coordinator in that, as I mentioned. So this resulted in a cluster, and if you look very closely, you can see that the word cloud here has become the word cluster here. So this is the continuation of these efforts within, sort of outside of project funding. Once the project finished, we carried on the work within this kind of umbrella of ANOSC. And in this, we're involved with a broader scientific collection of scientific work with science clusters, 5 clusters there, covering things like astronomy, particle physics, and life science, social sciences ourselves, and the environment. So this is our engagement with EOSC, which is the Open Science Forum from Europe. So that's just in the way of a quick introduction. That's where I'm coming from. The open data. So I would say we're in the middle of a paradigm shift at the moment in the way science is being conducted. We're shifting away from the old way of doing science, which is more siloed, people working in individuals or in small teams, to much more collaborative and more open, or more of making the works more easily available. There is a definition from open science. It varies a little bit depending on who you talk to. This one from the OECD is quite widely quoted, although it's perhaps a little bit too narrow. People would interpret open science a bit more broadly these days. But one of the things that's quite nice from the Open Science website here is this: a publication is not finished until you publish the data. So this is you publish in journals, but you should also publish your data that underpins and supports your journalistic publication. That should be part of what you're thinking to do. And increasingly journals are insisting on that now as well. So open science is broader than just open data. I've just put this down again, just as in terms of context. So the top one here is open access, so the publishing in journals that allow people to read and appreciate and take on board the information without barriers, so freely available journal articles for open access. Open data is then the next part of that, using things like license and FAIR. We'll come onto those in a little bit. Open source software. I mean, software is very. I am a senior programmer within the Dcache software. Dcache itself is open source. I use open source myself. This is something I care a lot about, and I think it's very important. And this is also reflected here. Open hardware. This is, again, it's kind of a new thing that's come up, where people share the hardware designs, fabrication techniques. So this is something that's, again, come up relatively recently, driven by sort of new technologies, educational resources, making training available online. Something else we're involved in within PANOSC is providing a platform to allow free access to training material. And the last one is citizen science. So this is engaging with people, the general public. We had the good fortune to be able to do work in this area in the ESCAPE project, where we're working with the Open University from the UK on building up various projects using things like Zooniverse. So this, if you haven't seen this is very much worthwhile going to have a look and see. It's some excellent work going on there. So one of the cornerstones here for open science which open data comes from, or is part of, is this idea of sharing, that really sharing is the basis for which science works. It's this idea of standing on the shoulders of giants, making contributions based on the work of others. And that only really works if the results of science are available for people to work on, to base on. And data is an important aspect of that. If we contrast that with the traditional approach, or at least the approach that's we're trying to move away from, there's things like limited access to publications, which creates these barriers for people to try and understand and benefit from the work that's been done in various contexts and various research activities. Transparency, and this is something that's actually come up more and more recently. There's been cases of fraud that have been caught, and these are now easier to catch because there's a lot more transparency. But the other thing is that there's, even without there being actual fraud, there's a number of cases of scientific results that have been held as absolutely accepted within the particular scientific community, only for people then to have been unable to reproduce those results. And so there's a reproducibility, well, some people called it a crisis, where people are now looking at this ability to reproduce the results, which is a cornerstone of scientific method. And the transparency and the availability of this is at least highlighting this problem. Data hoarding, this is obviously open data related, and software, using proprietary software creates various problems. So we contrast that with where we want to get to in open science, making this knowledge available, faster innovation. If you can build up on what people, what information is readily available, then yes, you can avoid mistakes. You have new ideas. All kinds of beneficial things to innovate on a faster timescale. The transparency I've already mentioned, the possibilities of collaborating, because you know who's working where, who's got similar ideas that you can pursue, and together in sort of collectively finding some approaches. And the last one's actually also very important for sustainability. So science, and particularly public funded science, needs an engagement and an acknowledgement within society, with people outside in general. They have to see this as useful. And so one of the things at DESY we do is we have open days where we open up DESY to all of the people, to anyone who can come along, and we put everything out on show. We have everyone's there. We explain the work we're doing, how it's important, what the benefits are to the people there, and how this is very important to engage and make sure people appreciate the work that's going on, so that they can understand that. And this is another aspect of open science. That we are in this paradigm shift. It's not something. It's change, and change is always or can often be very challenging and difficult for people who are, particularly people who are used to the old way, or the sort of established way of doing it. And there are certain concerns, the questions people raise to do with, if I publish my data, then somebody might use my data without acknowledging it. The costs associated, publishing costs money. So if it's publicly accessible freely, then that cost has to be taken on board elsewhere. Things like data management plans. So there's a lot of questions out there. I think in the time available, I don't have time really to go into this in great depth, other than to say that there are people working on these things. There is this French publication. The publication's in English, but it's from this Open Science, Ouvre Science here, which is, I would strongly recommend. It's not a big thing. It's a very relatively concise booklet, which is freely available. So I would recommend going into there to have a look at those. One of the concerns that was sort of raised as something worth looking into is some of the kind of more legal aspects of open data, where this can get problematic. I have to preface this, I'm not a lawyer, so this isn't in any way legal advice. And I think that the general advice is, if you're not sure, then you should talk to somebody this is their job. So your data protection officer or whoever it is in your organization responsible for these kinds of aspects. But to give you kind of a flavor, the intellectual property is normally broken down into 4 aspects: copyright, patents, trademarks, and trade secrets. I think trademarks and probably patents don't really enter into open data. Trade secrets, that could be an issue depending on how I don't have any strong background in this, so I can't really comment too much on that. Copyright is the one that people mostly think about when they're dealing with open data. And here it's relatively, let's say relatively straightforward. You need to identify the ownership, and the owner needs to release that the data under appropriate license. So it's very important. So strong recommendation, or a strong statement: make sure you choose a license and make sure it's clear when you have made that data available, what that license is. I very strongly recommend that you do not invent your own license. Do not make something up. Use one of the existing licenses that have been developed and that people understand. If you do your own one, you'll just make things complicated or get it wrong in legal terms, make mistakes. So I strongly recommend do not create your own license.
Can I interrupt,
Yes, certainly.
Paul?
Yeah, please.
I think as well, if I'm not mistaken, mostly either the institute or the country may decide as well on the license you fall
Yeah.
upon, right? So as individual, you may not even have the choice of the license.
Yeah, so this is where the data policies come in here. So depending on who's paying the money, who's funding the work, they will generally have a say in things like choice of license. So if you have a decision, if it is your own data in some sense, not you may have some influence on the choice. So I would, if that's the case, then I would recommend a Creative Commons license. But obviously, yeah, I mean, if you have a data policy which says data is released under this particular license, then there's not much you can do about that, other than maybe to inform people that this might not be the best choice if you think that it's not the best choice. So there may be some discussion, but in the end, you have to follow the policy. So that's copyright. Another strong aspect is GDPR, which deals with the regulation of personal data. This is normally not a problem for data, but it can be at least a concern if you're dealing with provenance information. So how the data was prepared, who did what, where, then you might identify people. Similarly, sample information might include identity of people who prepared the sample, or that. So this is something where you might want to check if there's any personal data, how that's being handled, and it's being done appropriately according to GDPR. There's also, again, going back to, as your comment said, yeah, earlier about you might not be in control. But so one of the things the Commission is pushing or has a mandate for open science The data should be as open as possible, but only as closed as necessary. So for the legitimate interests of the researcher. So this is to put that in some kind of context for in our case, this is the idea of having an embargo period. So 1, 2, 3, 5 years, whatever period it is, where the data is no longer the data is not available publicly to allow the researcher a chance to develop and publish papers on, to do their work there before it becomes public. The other thing to mention here is the European Open Science Cloud, EOS, which you mentioned before, which is a funding and mechanism to support open science in Europe, with various projects and technologies being developed, services to support that, and FAIR, which is something I'll get onto in a little bit. And I think is another strong point is the involvement of industry in sort of data collecting activities or data processing activities. This is something where, again, it's actually, for me, we do this at DESY and we do this at the various LEAPS facilities in Europe. It's not something I'm personally involved in, so I can't really speak too much on this particular thing. But one thing I have noticed is that there's starting to be a trend, I mean, there's instances where commercial companies have started offering up their data as a kind of a commons available resource for people to use. So they've collected the data, but they see value in having this available more generally. This isn't common, but it is there are isolated instances of that happening. Just to give you some quick examples before moving on to FAIR data. So there are lots and lots of open data portfolios or databases. One of the perhaps the most famous one is the Protein Data Bank, which was then used, I think, by Google to develop the AlphaFold project, or within the AlphaFold aspect, to do with protein folding and to understand that. So this is since 1971. There's also other very domain-specific databases. So this is one of the nice things about working in this kind of X-ray, neutron and X-ray analysis facilities, is you have a very broad range of targets or items that you want to analyze from very much biological ones right the way through to material science on metals and batteries and all kinds of different things. So there's quite a wide range of open data available in terms of X-ray. So yeah, paleontology and human organ atlas being another couple of examples there of open data that's then available for people to build on. So FAIR, I'm going to go through this relatively quickly, but hopefully to leave time for people to ask questions if they have sort of questions on particular aspects. So FAIR itself is an acronym, so FAIR, which stands for Fairable, Accessible, Interoperable, and Reusable, as defined in the original Nature publication from Wilkinson. These have subsequently been broken down into these kind of different aspects here. So F1, F2, F3, F4 in the kind of in this Go FAIR project. They kind of tried to make it a bit more tangible. In order to, so this is how, so FAIR itself is how you make a data actually useful. So it's one thing to make data available, which is open data, but it's not necessarily useful out of the box. So you need to do things to make it useful. And the FAIR is kind of a guiding principle on how to do that. So first, you need to find the data. So this involves describing it so that you can search for it. This is metadata that describes the key aspects, and this is often domain specific. So you need a domain specific way of describing your data. Accessible, you need to be able to, you can call it download. I mean, it's not necessarily downloading, but it needs to be accessible so you can actually get it onto your computer to actually do any kind of analysis on it. Interoperable, again, it's in order to actually be able to use it, you need to be able to use the same kind of tools, which suggests a common standard interoperability. So that's also important. And reusable, then this is actually the enough information so that you can actually understand the context within which the data was taken. So if you have the data and you can open it up and it's a picture, but you've no idea what that picture means, it's not very useful. So you need the information there to actually do the analysis. So I'm going to go through the different aspects of surrounding things that support this kind of activity. And the first thing or first one here is on actually being able to get at the data. And for this, there's a couple of important things. One is having what's called persistent identifiers, persistent unique identifiers. And the idea here is that when you have a data set, you want to have a reference for that data set, so you can talk about this data set and no other data set, this one here. This is exactly what I'm talking about without any confusion. Otherwise, you might be talking about two different data sets, so it's kind of fairly obvious. So some people might use a URL, a web address for this. This is actually a terrible way of referring to data. URLs are notorious for being so link rot is kind of the term being used, where the URL is no longer actually resolves to the thing you want to talk about, because the service changes, the name of the changes, the name of the URL, the domain name and the URL changes, the path changes, and this is very difficult to keep live and up to date. So this is where persistent identifiers come in. There are several. For people, the prominent one is ORCID. And if anyone here has not already got an ORCID ID, then I would strongly recommend you go today to ORCID and sign up. It's free, it's quick, and you have an ID that you can use in all your publications and all your other work to tie it all together, so you can have a record of your research activities. I strongly recommend doing that. For institutes and for funding agencies, there's RAW. For a lot of other things like journals, publications, and data publications, for instruments, samples, there's DOIs. So this is kind of quite a broad range of things. So DOIs are you want a DOI for your data set. You also, I mean, you can see here up here, there's kind of two approaches. One kind of naive, I would say, approach is to say, yes, my data is available, just ask me for it. This doesn't work. They've tried, there's been numerous studies where people have taken these kinds of things at face value and said, okay, I will contact the author and ask for a copy of the data set. And it's in a lot of the times, the author is no longer working at that institute anymore, so the email address just doesn't work. In other times, they just didn't reply because they're presumably too busy. Other times, they've said, oh yeah, it's on this floppy disk, but I don't have any floppy disk drives anymore. Data availability by relying on people is demonstrated as not working. So you need a repository to store the data at, and we'll talk a little bit more about that in a minute, but that's just something there for your to put that in some kind of context. The other thing is policies. We talked about this earlier with copyright and the choices on the particular license being used, but it's also the time scale and the fact that the availability and the authorization, if you like, to release that data is also important. This is something within PANOSC and the LEAPS facilities we're working on. We've not reached full coverage yet, but we're working on there. And you see we've had considerable success with the various facilities listed there with an embargo period. Another thing is not to focus too strongly on data, but see this as part of a broader picture, data and research outputs. So this includes raw data and process data underpinning journal publications, but also the metadata. This is also important, and the metadata itself should be fair. There's the workflows that you went through to actually do the analysis from raw data to the data that's supporting the journal publications. That again, you should make open and freely available. Logbook software and so on. These are all aspects that you want to be able to identify with the persistent identifier, ideally, and link to so you can walk and identify what's available and how you got to the data, so the kind of provenance related information. I mentioned metadata as a way of finding data is also important for understanding the context of the data, so you can do the analysis. And this is something where it's rather domain specific. In our domain, we have various ones with Nexus. FITS also has information. So this, and there's Nexus is an international standard established by people volunteering effort from facilities throughout the world, and coming together and agreeing a standard way of describing the aspects of an experiment, so that they can, looking at the data, you can actually understand how to do the analysis. A quick little aside. So I mentioned earlier, right at the very beginning, that one of the things I'm involved with is a thing called PANET. This is just as an illustrative example of why metadata is hard. So within the Expanse project, we had a look around and we found that there was a gap, something that would be very useful to know, which is simply which experimental technique was used when gathering data. So we had there are various techniques. It's very relatively standardized. So if somebody is talking about SAX or WAX or PCX or XPCS or one of the standard ones, then everyone knows what they're talking about. But you might want to search for particular type of data, and there you would need to understand that, well, SAX, WAX, and XPCS are all spectroscopy related techniques, whereas PCX is an imaging technique. And that's something that if you wanted to look for spectroscopic data, you would want to include these SAX, WAX, and XPCX data and the other sort of spectroscopic techniques, but you would want to exclude the imaging ones. So this is something where the hierarchy matters. So this was what we were setting out to solve. However, there's a lot of detail in sort of the sort of people-related things, getting this ontology adopted, the facilities, getting engagement, chicken and egg, handling changes in a robust way, sustainability, and so on and so on. So there's a lot that goes into this, and it's quite hard to do beyond simply the knowledge management aspects of keeping track of things. So the recommendation here is don't invent a new vocabulary unless you're sure that there isn't any of the existing ones. If you don't know, there are places you can go. So fairsharing.org and the DCC's metadata list will give you some starting points to look for metadata standards that you can use when describing your data. Data formats are also important. This is, again, if you want to allow people in sort of the eye interoperability, then adopting a standard file format allows you, the toolage will then be available for you. Here are some examples. There's sort of traditional ones, and there's new, uh, more sort of data object store kind of ones like ZAR that are becoming more popular. The general recommendation, look to your community. What's the standard that you're using? Don't deviate from that unless you've got very good reasons for doing so. Again, there's a link there for further reading that's useful. Another thing, I mean, I don't know about for other people, but certainly when I was at university training up as a scientist, physicist, one of the things that was kind of very much emphasized was writing things down in logbooks so that you have a record of what happened, which you can then refer back to. This is now transitioning to e-logbooks, which are an online electronic version of these, which bring certain advantages in terms of collaborative work, which is something that we're kind of adopting within the PANOS community here at the different photon neutron facilities. But it's also interesting to look at this as metadata that you can then link back to in your open data publications. Here's the data, and here's the logbook that was used to generate that data, or the record of how the experiment where that was generated. So that's another interesting aspect where bring FAIR into it, so you can understand the context. I've mentioned open source software before. I also use the word free software. Some people call Libre software. This various philosophical aspects to do with or ethical aspects to do with software and software development. But beyond that, the other thing to emphasize is that there is a lot of work a lot of experience coming from the programming community outside of science on best practices. And you really want to follow those best practices and be informed by and adopt those best practices. Things like version control systems, CI/CD, sort of testing frameworks, and so on. These are people have learned over the years. These are very useful for when you're developing software. So don't make the mistake and actually of ignoring these things. That they are important. And obviously, when you, as this is FAIR, you want to then cite your software in your publications so that you know the work that went into that. Just more generally on toolage and languages and these kinds of things. So Python is I mean, I don't know in corrosion, but Python just generally is very popular in science. Though there's an interesting trend at the moment towards Julia as a more higher performing programming language, that is something that gives you avoid some of the performance penalties you get from Python without having to go back to using C++, or C or C++. So this is now gaining a bit of interest there, which is interesting to observe. In terms of environment, Jupyter notebooks are now increasingly seen as a viable, reasonable way of doing analysis. This is quite interesting because at the start of the Expanse and PANOS projects, these were kind of dismissed as not really compatible with scientific research. But now, 5 years later down the line, these are now widely accepted. So that's an interesting trend there. Another thing you may have heard of is the Data Management Plan, the DMP. This is a document that sometimes interactive document, which documents what you are going to do with your data, how it's going to be collected, how it's going to be managed, what are the steps are for that use. For us in photon neutron facilities, the DMP is mostly about avoiding surprises. So if you collect if a large amount of data. You don't turn up with a thumb drive and say, oh, I'll just copy this and take it home with me. That's not going to work. And so these kind of DMPs allow you to plan ahead and understand what it is, what your responsibilities are, what you can expect, and how that should work. They're increasingly being seen as a useful tool to make sure that the data is managed, curated correctly, even to the point where DMPs are now being, there's some research work investigating how you can use DMPs as a way of collecting metadata, which then becomes used in the when you publish data. So this is all, not just on data management, also about capturing information. If you want to know more about DMPs, there's a rather nice, rather fun video that was prepared under the EOS Future project, which is available on YouTube. So the link's there if you want to see that. Then the 11th of the 12 steps that we've got here for VAIR data is finding a repository to put your data into. As I said before, having something like email the authors for if you want to have the copy of the data. This doesn't work. It's been proved this doesn't work in practice, however well-meaning the people are. Instead, you need to put your data somewhere so that it's archived and available for a long term, for a suitable long term. You may have domain-specific repositories that make sense for this data of a particular type. If you're unsure, you can go to these kind of registries of repositories. So I think the most, the widest one of these is Read3Data. So if you don't know, you can have a look there, see if there's somewhere you can put your data that's reasonable. And if you don't find anything, there's this service called Zenodo, which is it's actually hosted at CERN, which provides I think it's about 4 gigabytes that limit. So if your data is 4 gig or less, then you can upload it to Zenodo and they take care of it for you. So there's that data repository. When you're storing data, the final one here, you would need to consider how much of your data is, what that data is actually needed, and what you should take care of and store. One of the things that we kind of talk about is this kind of data deluge. The detectors that we have are constantly being improved, in terms of the size of the detector, the bit depth that they provide, and also the frame rate. So they're producing ever more data volume, data velocity, which gives challenges in terms of processing that data, but also brings up challenges in terms of how that data is stored longer term. So with these kinds of challenges, you may need to think carefully about what data you actually want to store and make open, because if you have large data sets, then it may become prohibitive for anyone to download that data, for example. So you need to think about what makes sense for potential future use. One thing I've got here, just as a little fun thing, sort of leading into one of the later talks on AI. So one of the things that we're trying to do, we are doing, is moving in towards automation. So within a particular field of activity, micrometallic crystallography, this is something where it's very, very standard. All of the aspects of this are optimized and kind of well established. So this is something that is almost a production line process now, in terms of getting data out. That's in a particular experimental technique and a particular activity. And there's a sort of on our technical roadmap is this idea of enhancing this for other techniques to provide a more to faster turnaround to support this kind of operation and from that we get large amounts of data that's fairly standardized, fairly curated and well annotated. That is then something that you can use that for lots of different things, but one kind of very popular thing at the moment is AI, particularly machine learning models being trained up on available data. This is, in order to support that, you need freely available, curated, well annotated data. Well, that's open data and fair data. So this is exactly what we're producing. So as people producing that data, you're in the perfect place to make sure to support that use in the future, so that you can have a conversation or a collaboration with the people developing these AI ML models. What kind of data makes sense? What information, what metadata do you need in order to support these training activities? And these could be yourself. So the models could be your own activities. But again, this is about establishing standard approaches and consensus across different communities. The final one here, this is going back to one of the previous ones, the protein database, the PDB. So you can see down here in the little orange dot is the PDB experimental results. And this was used to train AI to understand the protein folding problem, to understand, given a protein structure, how it will evolve, how it will actually end up in 3 dimensions in the structure, which has a very strong impact on the functional activities of that protein. Before AlphaFold, this was an unsolved problem, so you needed to experimentally verify or identify the structure. But with AlphaFold, there's now at the point where I think it's considered a solved problem. If you have a protein structure, you can then ask the machine, the ML model, what is the 3-dimensional structure you predict for this protein, and it will give you an answer which is with reasonably high confidence level matching reality. So this is has been a huge improvement for various areas of medical research, sickle cell, for example, other areas as well. So this is something where there's been a real societal benefit from open data and the AI ML activities that were possible only because of that open data. So I'm going to wrap up now, hopefully give people a chance for a few questions if we have time. So from my perspective, open data is about establishing common good, something that's available for people to use, build on. It's a paradigm shift from older ways of doing, with all of the challenges that this kind of paradigm shift entails. It's not easy, but you're not alone. We're all walking along this path together to try and build up the availability of scientific data. Fair data, I've gone through some of those in some aspects of those. This is one way of looking at or thinking about fair, is how do you make the open data actually useful for other people? Just publishing the data isn't enough. You have to do things. You have to curate it and make it available in a way that people can actually consume it and use it. And bearing in mind that the other people who might want to use that data is yourself in 5 years' time. So if you go back 5 years, can you remember all of the intricate details of the experiment that you set up and the details of it? Maybe not everything. If you've curated the data so it's fair, then in 5 years' time, you can then just use the data. So it's not just for other people, it can be for yourself. However, the other thing to sort of emphasize, to point out, this doesn't come for free. This making data fair, it requires time and effort, and for that to be sustainable, the community of scientists need to find a way of assigning value, make it worth the effort, so that this needs to be recognized. This is starting to happen in different fields. People are starting to look at this and saying this is something that we will acknowledge and actually take into account at a funding level. But we're not kind of there completely yet. The other thing is we're seeing, I think anyway, an increasingly data-driven future. This is kind of the second paradigm shift, where we're seeing, because there's a highly strongly available, highly available data, open data. We're seeing things like machine learning becoming more prevalent, and that's so that's very interesting to see. And this is something I think will impact on this various scientific workflows moving forward. So that's it. I hope that's useful. It's a big vote of thanks to Andy. Very nice to have Andy, who shared his talk on a similar topics on the role of scientists in making data fair and reproducible science from the Hercules European School. A lot of the material presented here comes from Andy, so it's a huge thanks to him and various other sources here that I've mentioned.